We started to talk for a moment in the last class about gradient selection experiment. So it makes sense to talk about gradient selection. The mic not work? Oh, that's probably on. Too many things to So at the end of class we talked briefly about the gradient selection of apartment filter cozy. And so it makes sense to talk a little about gradients. So your boss spends an enormous amount of money to buy a magnet with a very homogeneous field. And then with the gradient pulse, we're going to temporarily render the field inhomogeneous, but in a controlled way. And in the simplest case, when a gradient pulse is turned on, a coil inside the probe is energized. And that coil is wound in such a way that it produces a magnetic field along the z-axis. And the amplitude of that field varies from 0, the middle of the sample volume, in either direction. So it can either increase going above 0 and decrease going below, or increase going below, decrease going above, depending on the polarity by which one charges the coil. That's under our control. And that's called the Z gradient, and it's indicated here then by this. An additional B field along the Z that depends, whose amplitude depends on the position along the Z, unlike our B naught field that we hope is identical to all positions along the Z. And that means that the instantaneous precession frequency for some transverse magnetization at a particular Z location depends on the sum of these. The field in the way the probes are built varies linearly along the Z. So capital G sub Z here is called the field gradient. That will be something like Gauss per centimeter. And then Z is the position. So the product of the two is a magnetic field. But it depends on the V. And then by our usual arithmetic, we have during the pulse the normal Larmor precession, and then some additional precession that depends on the size of the gradient, the size of the magnetogyric ratio, and the position that that particular spin has along the z-axis. So if we turned on a gradient in the, oops, get to this. If we turn on this gradient and assume that we were on resonance, then here's what we predict. If we have X magnetization, we turn on the gradient for some time, and we'll get precession at whatever that frequency is. So we'll get a cosine projection of the IX operator, and since I have this minus sign here, I'll get a projection onto the minus IY operator. I can use a negative amplitude on the plus IY. And if I want to, I can resolve these two into their plus and minus components so that I end up with I plus gets a z-dependent phase factor, and I minus gets a z-dependent phase factor in the other direction. And the critical point is that if the gradient is strong enough, these phase factors as a function of z will vary over all possible angles, possibly many times 2 pi, but certainly is 2 pi. So if we end up with averaging the signal over phase factors that cover all angles between 0 and 2 pi, then that signal will be 0. Because for every Ix component pointing along the plus x direction, there's going to be one pointing along the minus x direction. So after the gradient pulse, if the gradient pulse is strong enough, if we turn on the receiver, we won't see any magnetization, we won't see any signal. And what happens pictorially, I keep meaning to make a better picture, but we start, for example, with Ix magnetization, and before the pulse, if we think about magnetization along the z-axis, every little sub-ensemble along z is pointing in the same direction. Right? After the Ix pulse, or in this case after an Iy pulse, all the magnetization is along x. Now we turn on the gradient, and what happens? Now, the one in the center, nothing happens to. But ones above start to precess, and they acquire some phase that depends on where they are along the z-axis. So if I look down from the top, it's easier if I look down from the top. X, Y, and now one little component stays, another one rotates to here, to here, to here, to here, to here. So averaged over the whole sample, I get 0. You can think of it as taking, say, a strip of paper that looks like this, and now twisting it into a helix. The top rotates, say, in the clockwise direction, and the bottom rotates in the anti-clockwise direction, and you get turns of the helix along the sample, and then averaged over the projections, you'll get 0. So here's what we would see as a function of how long we turn on the gradient. If the gradient isn't on, we just have X magnetization. And when we turn the gradient on, there's now going to be precession of the magnetization during the pulse. And if it's on for just a very short amount of time, we still have some signal left because the magnetization components don't precess very far away from the x-axis. Some go a little bit towards the positive y, the others go towards the negative y, but there's still a projection along the x-axis, so we still have some signal. But as you can see, that signal damps away as the gradient pulses on for a longer and longer period of time, because now we're winding the magnetization up in this helix, covering all the angles. And the dashed line is a sinc function, and that kind of hits the maximum here. So if we turn the gradient pulse on long enough, and say turn the receiver on here, we'll see no signal. Now this will depend on the geomagnetic ratio and the coherence order. So single quantum magnetization precesses the alarm frequency. Double quantum coherence precesses the sum of two frequencies. So if both frequencies are positive, double quantum coherence is a phase twice as fast as single quantum. On the other hand, if the two frequencies have opposite signs, then dephasing might be very slow. For example, zero quantum coherence, or zero quantum coherence, I1 plus, I2 minus. If those are both hydrogens, they both have the same gamma, and that means their frequency difference is only the frequency difference of their chemical shifts. And dephasing will become very inefficient. For single quantum coherence on a solution probe, a typical gradient strength would be something like 30 Gauss per centimeter. And that means that a few hundred microsecond long pulse is enough to dephase proton magnetization if one sits down and works out the arrhythmia. Gamma for nitrogen is much smaller, so it takes longer to dephase nitrogen than it takes to dephase hydrogen because of the difference in gamma. The frequencies are smaller. But zero quantum magnetization, homonuclear zero quantum magnetization is a problem. One of the things that we said gradient pulses were very good at was to be suppressing artifacts in the spectrum or getting rid of coherence orders that we're not interested in some experiment, but they might not work very well for zero quantum coherence. And now the idea is, how do we use gradients for coherence selection? Well, when we apply the gradient pulse, wind up the magnetization, and now we have no net signal, that's not really a saturated system. A saturated system, there would be no net signal because all the magnetization components were randomly pointing in different directions. Here we've twisted up the helix. We can untwist the helix by applying a gradient with the opposite sign, polar, charging the coil with the opposite polarity, electrical polarity. Or we could apply a 180-degree pulse, which reverses the sense of rotation of the spins, and then apply a gradient with the same polarity, and now the spin will unwind, the helix unwinds, and the signal comes back. So this is called a gradient echo, when we use the second gradient to undo the winding up of the first. And because the precession during the gradient depends on the coherence order and the gamma, we can use that to select for coherence order changes. So if at some particular point Z in the sample, some magnetization acquires a phase phi sub I, and then later on we apply a second gradient, there'll be a phase, I should say, phi sub F, phi final. If we want to detect the signal, the sum of these has to be 0, so that the net effect of the two gradient pulses is canceled. And that says we can adjust, for example, we could pick out what coherence orders we want, PI and PI. We can make use of differences in gamma. We transfer magnetization between, say, hydrogen and nitrogen. We can change the strengths of the gradients, or we can change the length of the gradients. We can manipulate anything we want as long as the sum is 0. S here, by the way, is a shape factor. So all we really care about is the integrated area of the gradient pulse. And frequently, gradient pulses will be turned on with some shape so that you don't have a very strong transient when you turn on a square pulse. In the old days, it's less of an issue now. In the old days, on a Bruker spectrometer, the gradient coils weren't so mechanically robust, and it was possible to turn on a strong enough square gradient that the transient impulse magnetic field forces would break the gradient coil loose. It's much less of a problem now. People are still in the habit lots of times of having to shake and round the edges a little bit. But it doesn't matter to the math, because it's just the integrated area that's important. And usually, when applying pairs of gradients, if they're shaped, you'll use the same shape for each member of the pair. and then you don't have to worry about matching the intervals in the shapes. So here's just an example in which we might want to select +2 quantum coherence being converted to -1 quantum coherence during some pulse. And to do that, if we apply a gradient pulse for time t to the +2 quantum coherence, we'll have to apply a gradient pulse for 2t for the -1 quantum coherence. This should probably be a 90-degree pulse, by the way. That's the type. So here is our example. And now you can see why we can only select +2 or -2. Because during this first gradient, the +2 quantum coherence will wind up into a helix in one sense, and the -2 quantum coherence winds up in a helix in the other sense. So when we apply the second gradient, if we unwind the first helix, we continue to overwind the second helix. And if we choose to unwind the second helix, we'll overwind the first helix. So we can't detect +p and -p at the same time with the gradient. One of those will just get wound up even tighter in the helix by the second pulse. Only one of them can be unwound. So that's I think all I'll say about gradients right now. And then, by the way, Tuesday there's no class. Is that what we do? At Wednesday. Wednesday there's no class. There's also no class on Tuesday. That's my statistics class. So Wednesday will be no class. Thursday will be processing with NMR FX. And then I think after that, there might be introduction to tensors.
Yeah, anisotropic interactions, rotations, tensors. And something else about the schedule, just a little bit further out, but an optional recommended workshop for everybody in this class will take place at a non-usual class scheduled time. Monday, May 7th. So that's after final, so we can't grade you one. But I want you to look at your calendars and write that down, okay? Because it's going to be about numerical simulations and some of the things we talked about with a guest lecturer who developed a remarkable set of program. Okay, so that's Monday, May 7th. It's not required. It's just recommended. So Wednesday, there's no class.
So with the rules that we have now, we in principle can analyze all sorts of pulse sequences. So for example, you probably recognize this sequence as being an HSQC sequence if I put in delays. There's now 1, 2, 3, 4, 5, 6, 7, 8, 10, 11 pulses. But we have with our rules for evolving the operators everything we need to do to analyze what happens. Because I simply start with IX magnetization, ask what happens to that during this first pulse. And I know the rules for that. If that's the next pulse, I'll get -IY. Then I have some delay here, and I evolve that IY magnetization for that delay. I evolve the magnetization under the chemical shift and under the scalar coupling. Then I have two 180-degree pulses, and I apply those two 180-degree pulses to the operators that came from this first period. I take that answer, evolve it for another time period under the chemical shift and scalar coupling Hamiltonians. I take that answer and apply two 90-degree pulses. I take that answer, evolve it during, actually I shouldn't have this here. Evolve it during this time period, apply to 180, evolve during the next time period, apply 2 more 90s, so on and so forth. So I break a complicated pulse sequence up into the parts in which some part is a pulse and some other part is a delay. And because I assume I'm in the weak coupling limit, I can apply the chemical shift evolution first and then the scalar coupling, or the scalar coupling and then the chemical shift. That doesn't matter. If I want to, I assume that the pulses are short. If I'm doing this in my pencil and paper, so I'll ignore relaxation effects during the pulses. I'll ignore scalar coupling evolution during the pulses. If I need to add relaxation in, I'll usually just add some phenomenological damping by R2 whenever I have transverse magnetization for some time period. And then, just pick some reasonable values for R2 from my experience if I want to know how much signal I lose. So I can do quite a bit with what we already know. Now, I may want to learn some tricks so that I can reduce the workload that I have in analyzing these 10 pulses. But I at least have the tools. So what can go wrong here? Well, first of all, I may want to know more about relaxation effects than assuming some block like T1 or T2. So I may want to know much more about the details of relaxation processes. But the other thing that can happen is I might need to turn on an RF pulse for times that aren't really short compared to either relaxation or to the scalar couplings. So once the pulses have a length that becomes comparable to either the relaxation rates, 1 over the relaxation rate, the relaxation times, or 1 over the scalar couplings, there'll be relaxation during the pulse, there'll be scalar coupling evolution during the pulse that I need to take into account if I want to get an accurate understanding of the experiment. Now, the problem that will happen with both of those is the mathematics becomes very complicated, and we may want to eventually switch to more numerical methods. And as Ann said, on May 7th, there will be a workshop on numerical methods. But somewhere between our simple approach, recoupling short pulses, which is usually called the product operator approach or product operator formalism, and doing purely numerical calculations, we might hope we can learn something, but there may be methods in between those two limits. So the first case I'll talk about a bit is oxy transfer. And a Toxie experiment is designed to break out of the weak coupling limit, to restore the strong coupling limit. Hopefully you'll remember from when we introduced scalar coupling, I said that the weak coupling limit would occur if the difference in chemical shifts between the coupled spins was large compared to the J coupling. So if we want to have evolution occur under the strong coupling Hamiltonian, we have to get rid of the chemical shift difference. The J couplings are whatever they are. So we have to eliminate all or most of the chemical shift difference between the coupled spins. So how do we eliminate chemical shift? Right, we do spin echoes. And in this case, the spin echo, the delay in the spin echo would have to be short enough that there's no J-coupling evolution during the delays. Because if we allow, or if there's not chemical shift evolution, substantial chemical shift evolution during the delays. Because once the chemical shifts start to evolve enough that the two spins start to develop a significant phase relationship between the magnetization components, then we're in the weak coupling limit. So if this is to work, we would have to apply a string of 180-degree pulses where the delays are short compared to the chemical shift difference. And you can see the problem. The chemical shift difference, say between the H alphas and NHs, is about 4 parts per million. On a 500, that's 2,000 hertz. 1 over 2,000 hertz is half a millisecond. So we have to apply pulses much faster than half a millisecond. And this was done in the early days. In the beginning of trying to do these experiments, people had two ideas. One was just to turn on a continuous wave field, which is called spin locking, and the other was to do a train of 180 pulses with a very short spacing. And these both work kind of. They worked enough for people to get initial papers published, but not well enough to actually be useful. Because you have to turn on, in the CW case, you have to turn on a quite strong field. And if you apply a train of pulses, the pulse spacing has to be so short that now you're turning on a full power RF pulse at a rapid rate. And either situation was either too hard on the electronics or caused way too much heating and was too hard on your sample. So there were initial papers about doing this, but practical application required invention of ways of averaging out the chemical shift interaction with minimal power, and it would be broadband, because, of course, if we just turn down the RF power, the first thing that happens is we have very strong resonance offset effects, so that a 180-degree pulse on the alphas is no longer a 180-degree pulse on the PAs. So just turning down the RF power by itself doesn't work. You have to do something more sophisticated. In any event, if we said that we had the strong coupling Hamiltonian, we could then try to work out what happens with evolution under the strong coupling Hamiltonian. And it turns out if we just think about two spins, the strong coupling Hamiltonian would be, now I can't remember if I use INS there, it's equivalent to INS. The strong coupling Hamiltonian would be I dot S, or 2I dot S, 2IX SX plus 2IY SY plus 2IZ SZ. And then normally we would think of our evolution as depending on I, H, tau, and this would be E to the I, 2 pi, I dot S, and we have to ask, what's the exponential matrix representation of this dot product? Looks pretty complicated, but for two spins, we're lucky because it turns out, which you can work out, that IX SX, IY SY, and IZ SZ all commute with each other. And if they commute, the exponential of the sum turns in the product of the exponentials of the individual terms. So then we can work out term by term what happens. We don't have to take this full sum and work it out all at once. That's only true for 2 spins. So we'll be able to do a pencil and paper calculation here easily for 2 spins, but these commutation relationships break down for more than 2 spins. Stefan Glosser managed to solve these equations for 3 spins, and then in somewhat heroic but thankless effort, solved them for 4 spins. And I think he proved you can't do it in closed analytical form for 5 spins. It's interesting that 3 spins, well, for 2, 3, or 4 spins, you end up with equations that look like the coupled pendulum in physics. And Stefan likes to make little toys, so he sometimes shows a toy with a series of pendulums that are coupled together with rubber bands, and he sets them swinging while he talks about the taxi experiment. And you can see amplitude of the pendulum balls transfer from one to the other. One starts out stationary, the other one is swinging, and after a while, the first one is stationary, the second one is swinging. As magnetization, as it were, gets transferred through the spin system. So, but with this simplification, we can ask what happens to some operator, spin operator, acted on by IXSX, acted on by IYSY, or acted on by IZSC. It says using a previous result. I don't know where that came from, but we had our rule that if we worked out the commutators, we then would know what the evolution was. So here, I want to know what happens to IZ magnetization. So IZ magnetization, I work out commutators and end up then with this evolution rule. That IZ, acting on by a Hamiltonian that has the 2-spin operator IYSY, evolves to IZ cosine zeta plus 2IXSY sine zeta. And then I can work out what happens with IXSX, and I get a different evolution. And I can keep playing this game and work out all my rules. What happens to IZ magnetization acted on by 2IZSC? Here I worked out rules for IYSY, IXSX. What happened to IZSC? That was part of my dot product. No change, right? Z commutes with Z. So the Z operator doesn't have any effect to that. So if I have the strong coupling Hamiltonian and Z magnetization, I'll get evolution of these 2 parts of the Hamiltonian. And the Z part won't have any effect. So the net effect will be, when I work this all out, is IZ magnetization will evolve under the strong coupling Hamiltonian to give me a somewhat more complicated picture than I had before. I get IZ magnetization with the cosine square dependence at Z magnetization, and then some zero quantum coherence arises as well. All of these sinusoidal dependences, and I can do the same thing for SZ magnetization and get the symmetric result. So IZ magnetization gets transferred to SZ magnetization. SZ magnetization gets coupled, transferred to IZ, and there'll be flow back and forth between the 2. If I had 3 spins, I can't work out the analytic results, but it's probably easy for you to see, since the first coupling transfers IZ magnetization to SZ magnetization. If that S spin was coupled to an R spin, then the SZ magnetization that's building up is going to start to transfer to the RZ operator. And if the RZ operator is coupled to a KZ spin, will get transfer again. So the interesting thing about transfer under the strong coupling is you can get multiple hops from IZ, SZ, RZ, and the magnetization fans out in some very complicated way through the entire coupling topology of the spin system. That's different from the cozy experiment. The cozy experiment, we only got transfer from one spin to its partner. So the free precession scale of coupling, the weak coupling, only let us transfer from I to S. We didn't get from I to S to R. Now with the Coxey experiment, we can go I, S, R, all in one experiment. And that's why it's so popular. Now it's also the case that when I come to detect this signal, say the SZ signal here, I'm going to have to read that out by converting it to transverse magnetization with a 90-degree pulse. So suppose I apply a 90-degree pulse, this becomes, say, SX magnetization. What's the line shape going to be? Absorptive or dispersive. The absorptive, and in fact, both the diagonal and the crossbeam will be absorptive. And then, what about the multiplet structure? If we have IX or SX, what do we expect for the multiplet? In phase or interphase? Be brave, speak up. Antiphase has the two components in opposite directions, the two multiplet components, and that came when we had a Z operator, 2IXSZ, because SZ would be the same as S alpha minus S beta. And if we don't have anything here, IX magnetization, for example, we can think of it as IX magnetization times the identity operator, and the identity operator is S alpha plus S beta, and the two components have the same sign. So these are in-phase absorptive doublets for both the diagonal and the crossbeam. And that means, first of all, we don't have to worry about the dispersive tails. And secondly, we have in-phase multiplets. So as the molecule gets larger, the multiplets don't start to cancel each other. And in the cozy experiment, as the molecule gets larger and the line width grows, the positive and negative lobes of the antiphase signals start to overlap and cancel each other, which is why the cozy stops working when you go to a larger molecule. But here, the signal is in phase, so one can expect this to work on larger molecules, which is a pretty good thing. What about these guys, these signals? When I apply a 90-degree pulse, we have to worry about what happens to this zero point. So we'll come back to that in a moment. Now the problem of how to generate the strong coupling has been attacked for many years. So CW experiments didn't work very well. Strings of 180-degree pulses didn't work very well. The first schemes that didn't work we're using schemes that were normally used for decoupling. So we haven't talked about decoupling yet, but decoupling sequences were developed in order to collapse the J coupling, say between carbon and hydrogen. So if you're recording the hydrogen spectrum and you have carbon-13s and nitrogen-15s in the molecule, one gets doublets, and spectroscopists wanted to collapse those doublets into singlets in order to improve resolution. And the same problem came up. You could collapse with very strong CW fields, say applied to the carbon spectrum while you recorded the proton spectrum, but it wasn't very practical. And schemes started to be developed that would decouple with less and less power, better and better performance over broad bandwidth and low power. When the Toxie experiment came up, I think it was really bad backs had the idea of trying decoupling sequences in the Toxie experiment. It initially seems sort of silly in that you have an experiment, you have a pulse sequence that you think of as averaging the J coupling to 0, and now you want to use that same sequence to average the chemical shift to 0. But it turned out that it worked, and when I started as a postdoc in '89, people were using Waltz for doing Toxie experiments, and Waltz was at the time one of the best sequences for doing decoupling. The Waltz sequence, which probably Anne may talk about, was developed out of a family of sequences where what's called average Hamiltonian theory, which I know Anne will talk about, was used to try to get approximate solutions to these more complicated evolution under more complicated Hamiltonians than the weak scalar coupling. And people had very elegant ideas for how to improve approximate solutions so that if you had a solution that worked somewhat well, you could iteratively improve it. So there was Waltz 4, and then Waltz 8, and Waltz 16, Waltz 32, Waltz 64 were iterative ways of improving the primitive sequence to make it perform better and better. And there were symmetry reasons why one expected these schemes to work. But somewhere around 1990, 1989, the approach started on, let's forget about analytic solutions or solutions we understand. Let's just turn a computer loose and tell the computer we would like the chemical shift to be averaged to 0 over some bandwidth, or we would like the scalar coupling to be averaged to 0 over some bandwidth, and just see what a computer came up with. So what's shown here then are a series of these that were designed specifically for doing Toxie transfers as opposed to doing decoupling. And once the focus was on what was essential for doing Toxie transfer, one could find more efficient sequences so one could get better performance with reduced RF power. So what happens in this experiment? So here's a 90-degree pulse, followed by a T1 evolution period. So that's simply to let the chemical shift allow for the spin, so we have their frequencies in the first dimension. And of course, the scalar coupling will evolve too. That's not particularly interesting. This pulse then will put magnetization, some of the magnetization up onto the z-axis. And then historically, there was a little delay in order to allow the RF power to be switched to the power that would be used then for what's called now isotropic mixing, where we'll turn on one of those sequences that generates the strong scalar coupling. Nowadays, one might well put gradients on during these delays to help clean up the spectrum at the end of the day. So now what happens here is an RF field is turned on for times comparable to 1 over the J coupling for proton work. If you only want to transfer, say, by 1 hop, that might be quite short, of order 25 or 40 milliseconds. If you want to get transfer further out into the spin network, this might be as large as, say, 70 or 80 or even 100 milliseconds until you run out of signal because of T2. There's going to be losses, actually losses in here from what's called T1 row. And then after this is over, the magnetization has been transferred around to the other operators, and we have to pulse to bring the Z magnetization down to the transverse plane. And then here's one of these little hot echoes, just to get a good base plane that we talked about yesterday. Sometimes people use that, and sometimes they don't. Because we have the magnetization on Z, and could apply a gradient here, this is sometimes called a Z filtered Toxie experiment, because we're trying to dephase magnetization that depends up on Z. This is called isotropic mixing, because we talked about transferring Z magnetization from IZ to SZ. But some of these sequences will also transfer X magnetization to X magnetization at the same time, or Y magnetization to Y magnetization at the same time. They don't care what the starting orientation of the magnetization is. And in some experiments, one will make use of the fact that one might transfer both Z and X magnetization at the same time, and therefore gain some signal. That's maybe something we'll come back to. Others of these are designed just to transfer one of the components, say just the Z component. Because again, if the problem is more specific, there's generally a solution. It'll be more broadband or require lower power. So these sequences, for example, DIPSY is isotropic, but FLOPSY was designed really just to transfer Z magnetization. If you go to the spectrometer and open up a file that's labeled DIPSY, you'll see that it's just a large number of pulses with rather bizarre-looking flip angles and phases that jump back and forth between X and minus X. And the phase modulation and the modulation of the lengths of the pulses is what came out of the computer calculation to make this work. If you open up something that's labeled like worse, you'll see that the amplitudes of the pulses are being modulated, as well as phase and duration. So again, that point in the beginning, one's just modulating the duration of an individual pulse before you change the phase. And now you say I'm looking to modulate the amplitude as well as phase, one can potentially gain more control over the system. And now, with numerical approaches that come from what's called optimal control theory that was brought into NMR by Stuff and Glaser, the numerical outputs are completely unrecognizable. The sequences just look like bursts of noise, but they have the range properties that one wants. Very hard to look at those kinds of sequences and understand what's going on. If you look at the DIPSY sequence, for example, the lengths of the individual pulses seem arbitrary, but you can see that they repeat in blocks. And if you look inside of optimal control theory block, there's no apparent symmetry at all much of the time.
Question. So those sequences for solution, I've had some impact, it's not like it's teeny tiny machine. What's your impression about the impact for biopolymers where, you know, like relaxation is a big part of our challenge? The application maybe more in the small molecules or is there that big impact? Now I start with
Right, so if we talk about, the question really comes down to what's the size of the J coupling compared to the size of R2. Because during this sequence, during this block, there's going to be relaxation losses. One can try to arrange this so that you end up averaging T1 and R1 and R2. So the situation is a little better than you might think, but still, the relaxation losses become limited. And the proton-proton J couplings are, say, the H-alpha amide couplings range from about 2 hertz to 12 hertz. So you get to a protein of, say, 150 amino acid residues. These sequences are starting not to work so well. However, when we label with carbon-13, now the coupling between adjacent aliphatic carbons is about 33 hertz. So the transfers can be done much more quickly, and in 25 milliseconds, one can spread the magnetization pretty far. So these experiments work up to quite large proteins, particularly if the side chains are deuterated, because the main cause of relaxation of the carbon will be the attached hydrogen. So if you deuterate the side chain, these experiments are very powerful. The problem is, what signal do you eventually measure? And if you want to detect hydrogen at the end of the day, then typically one might relay the magnetization down to the amide hydrogen, dissolve the protein back in water, detect on the amide hydrogen, or there are methods for keeping the methyl groups protonated while the methylene groups are deuterated, and the methyl resonances are sharp because of rotation of the methyl group. So then you can relay magnetization down the side chain from the methyl groups and bring it back to the methyl groups or migrate it on to the amide and vice versa. Quite large proteins because you've beaten the relaxation by deuterating, and the coupling is pretty large.
Just to give an order of magnitude, so for those deuterated samples, you might need for an R2 versus the protein samples.
Oh, in theory, they should be about 36 times smaller relaxation rate. In practice, there's other effects from the deuteron, you don't get quite that much, but it's really profound. And you could do the experiment on the deuterated protein at least over 50 kilodaltons. I think Lewis has done them up over 80 kilodaltons. So that's usually not, for things, sorts of things, most things you're doing in solution, that's not the limiting part of the overall process of doing the project.
So like hundreds of milliseconds that were
for
T2.
Yes.
Hundreds of milliseconds that have been protonated for the few milliseconds.
That's right, about around 10 milliseconds.
Yeah.
So here then are numerical calculations for real spin systems. This is, I think, leucine or isoleucine, poorly labeled. And very poorly labeled. I've now forgotten which is which. So I think maybe B is in water and A is in B2O. It could be the reverse. So difference is whether there's an amide hydrogen around. But essentially what happens, let's assume for the moment that B is in water, and then the solid line is showing what happens if you start on the amide hydrogen and turn on the toxic field. Well, the first coupling is between the amide hydrogen and the alpha hydrogen. So one sees buildup of magnetization on the amide hydrogen, and that becomes maximal somewhere around 40 milliseconds of toxicness. But some is now starting to be relayed up to the beta. The magnetization is starting to accumulate on the alpha, starts to also then migrate to the beta, and then eventually to the gammas, and then out to the rest of the side chain. And at long mixing times, you can see we've moved all the magnetization out of the alpha. And it's all been moved onto the alpha and then spread its way out onto the other side chain protons. And you can get very funny behavior. So I don't remember if this is the beta or the gamma action, but you can see here that this particular proton ends up in a steady state where the magnetization flowing from it to the other spins is essentially offset by magnetization flowing from the other spins back to it. And so every amino acid has a different behavior in these kinds of calculations because of the topology. But fortunately, there are magic numbers that work pretty well. So 40 milliseconds does a pretty good job of transferring magnetization from the amide to the alpha, and something out around 60 or 70 usually does a reasonable job of getting magnetization further out into the side chain. 100 milliseconds is great for spreading magnetization to the side chain, but then you have to be a pretty small protein for the relaxation losses aren't intolerable for that. It used to be a major industry making these kinds of graphs, and sometimes people would record toxic spectra at different mixing times and try to look at the peak intensities to help identify what side chain they were looking at because of the different buildup. But that's pretty tough work because this is all convoluted with relaxation losses and different sizes of the coupling constants that we don't really know. The carbon experiments have made that much easier. So here's just some data from ubiquitin as a function of mixing time. And you can see mixing time is increasing in this direction. You can see the buildup intensity, for example, the epsilon of this lysine, you don't see at short mixing times. As the mixing time gets longer, you start to transfer magnetization. So this has been transferred all the way from the amide proton out to the epsilon proton in lysine by flowing from the amide to the alpha to the beta and gamma delta and finding the epsilon. But you can also see the overall intensity is going down because we're getting relaxation losses during the mixing. But these are very information-rich spectra because you see this whole favorable cases, the whole side chain. Now there's a tendency for assigning these peaks based on chemical shifts in the database. We now know a lot about the chemical shifts in databases. In the lysines, for example, in the database, one expects, as you can see here, that the betas are a little downfield of the gammas. But there are cases in which there's overlap in these distributions, and the toxie can be wrong. So one always has to be very careful if you're looking at a paper where people have assigned the side chain hydrogen just based on a homonuclear HH toxin, because the methylene groups in the wrong side chain, it's possible to get that wrong because of this overlap of the distribution. To really get that right, one wants to do multiple quantum experiments, but people don't do this so often anymore. It's so sensitive. I think the generation of people skilled in doing those experiments are now getting old and near retirement. On the other hand, the carbon-13 based experiments are quite definitive. Not just the protein is labeled. This isn't such an issue. Shoot, I was hoping. So if we looked at another part of the spectrum, we would also have the magnetization that started on the alpha and then was flowing both to the amide and out to the rest of the side chain. And if we look up at 3 parts per million, we would see the epsilon magnetization that's flowing backwards down the chain. It's all there, and that's helpful in working out the topology. If we wanted, for some reason, to only look at this part, then of course we could apply a selective pulse to excite only the amides. Or more commonly these days, we might have the protein labeled with N15, so then we only see this part of the spectrum because we've edited it by attaching to the N15. Yep? Right, so what goes wrong with the Poxy experiment? So what are the issues? So one issue is what happened to these. These zero quantum operators might well survive through the mixing sequence. Be created, or they're going to be created during the mixing sequence, and may not relax away. Zero quantum magnetization might have a relatively small relaxation rate constant. So at the end of Poxy mixing, we not only have these terms, we'll have some of these. And then what happens when we apply the 90-degree lead pulse? Well, these will get turned into, some component of those gets turned into detectable magnetization. And they're called zero quantum artifacts. They have an antiphase dispersive line shape, and they're sitting right on top of the cross peaks you're interested in. And they lead to very nasty distortions of the cross peak and can lead to substantial cancellation in the amplitude of the cross peak. They're a very bad artifact. Fortunately, in a protein bigger than ubiquitin, because the line shape is antiphase, they are almost always null by self-cancellation within antiphase terms. So there's a few cross peaks in ubiquitin at short mixing times where you can see the zero quantum artifacts. I thought I had a picture in this slide deck that I built, so I'll put one in for next time just to show you what they look like. But most all of you are likely to be working on proteins bigger than ubiquitin, so you may never see a zero quantum artifact. And maybe a decade ago, a graduate student called me in a panic to come look at their Poxy spectrum because of this horrible looking peak they had discovered. And it was, of course, just a run-of-the-mill zero quantum cross peak in the Poxy spectrum that they had managed to become a senior graduate student. Never see one. These days it's pretty rare. If you get the smaller proteins, things smaller than ubiquitin or peptides, small nucleic acids, the zero quantum peaks are a problem. And there have been a lot of efforts by people like James Keeler to try to figure out ways of using combinations of gradients and selective pulses to try to reduce by dephasing some of the zero quantum artifacts. And the problem we've already said is the chemical shift difference is very small in the homonuclear zero quantum peaks that are very hard to dephase. But James has had some fairly clever ideas over the years. And also some not so clever ideas like crushing a coil to make it very homogeneous. And you can do that in the box and crush the coil on the screen. The other problem that will come up is we have Z operators. And Z operators also cross-relax with through the dipole-dipole interaction. In the presence of an RF field, that's called the ROSY, rotating frame over Hauser effect. So Coxey spectra contain ROSY peaks. And those also can be a headache. For a macromolecule, when we come to talk more about relaxation effects, in a macromolecule, it turns out that the ROSY cross-relaxation rate and is a factor of -2 times the regular NOSY cross-relaxation rate. The ROSY rate has opposite sign as the NOSY, and in the limit of a large molecule, that ratio is known to be -2, a factor of -2. And that means it's possible to arrange the mixing sequence so that you average the NOE cross-relaxation against the ROE cross-relaxation and can get them to balance. So these are called clean Coxey sequences. And you have to maintain, as the magnetization vectors are being rotated during the sequence, that they average have a fixed relationship between the Z projection and the transverse projection. So sometimes that was done by inserting delays every time the magnetization came back to Z, leave a little delay. In other cases, it was done by adjusting the amplitude, so the average projection matches this requirement. So then the ROE and the ROE peaks can be known to a good approximation. So let me take a quick look at what I want. I do have a picture. It's just in the circle. There is a zero. And actually, it's not mislabeled. These are zero quantum peaks that come up in the NOSY spectrum for much the same reason. And there you can see them. It would look similar in the Coxey spectrum. So in the box are the NOSY peaks. The one labeled for R74 here happens to be between two residues. These are J-coupled, and you can't even see a NOSY peak between them. There should be a NOSY peak there. Or there could well be a NOSY peak there. They're J-coupled. They might be within 5 Angstroms of each other. I suppose it's possible that they're not. They're really all the way along the side chain. But certainly there's no sign of a NOSY. Up here, you can see there's probably a NOSY peak under there somewhere. It's highly distorted by the zero quantum. So that's what we're thinking the NOSY spectrum pretty much the same either way. And it comes from more or less the same number. So then probably we should finish up just by saying a few things about phase stable. In the interest of time, I'm only going to say a couple of things about it rather than going through in detail through the whole process or the whole theory. So now we're going to think of the density operator as being the sum of density operator components that have the same coherence order. Remember, the coherence order is the sum of the pluses and minuses with z counting as 0 in some operator representation. So this isn't an eigenbasis, because something like coherence order 0 could include I plus S minus, as well as IZ and SZ and 2IZS. So there's only 2p plus 1 terms in this expansion. If we have 2 spins, that means we can go from -2 to +2. There's 5 terms in the expansion, but we already know that our 2-spin system has 16 basis operators, because the matrices are 4 by 4 for 2 spins and have 16 elements. So this isn't the complete basis, so we can't use this as a basis, but we can use it for trying to understand how phase cycling is going to work. And the main result is that if we change some phase on a pulse, and that pulse transfers coherence from one operator to another, such that the coherence order changes by delta p. So suppose the pulse takes us from coherence order 0 to coherence order +1. If we shift the phase of the pulse, our coherence after the pulse will shift in phase by minus delta p times 5. This is telling you something you already know. It's just a different language. Suppose you start with Z magnetization, and we apply Z magnetization, we apply an X pulse to Z magnetization, we get minus Y magnetization. If I shift the phase of the pulse from X to Y and apply it to Z magnetization, I now get IX magnetization. I changed the phase of the pulse. I started with the same operator Z, which is 0 coherence, and my transverse operators for sum of plus and minus, I could resolve them into their plus and minuses. When I shifted the phase of the pulse, I shifted the phase of the transverse magnetization. This is just the mathematical statement of that. And to see it precisely, I would have to resolve the IX magnetization and the IY magnetization into the plus and minus components, and then I would see that the 90-degree shift in phase of the pulse, in that case, would generate a plus pi over 2 or a minus pi over 2 shift in phase of the operators. And the idea of phase cycling, then, is to shift the phase of the pulses, keep track of the phase that's accrued by the coherences through the whole pulse sequence, and then shift the phase of the receiver to compensate. So that if I generate, suppose I started with IZ, I apply an X pulse, I have minus IY magnetization, and I record that. Now I shift the phase of the pulse from X to minus X. the phase of the magnetization after the pulse is going to be IY. And if I want the signal to accumulate, I have to shift the phase of the receiver by 180 degrees, i.e. I have to subtract those two signals. If I don't do anything to the receiver, the two signals are going to null. So my idea is simply I keep track of the accrual of phase by the coherences through the pulse sequence as I shift the phase of the pulses. And at the end, I have to shift the phase of the receiver in order to accumulate the signals that I want and suppress the signals that I don't want by their relative phase properties. And the theory of phase cycling is just to make this easier to see. However, once you put the isotopes in, phase cycling becomes very simple because you're mostly selecting for transfers from 0 to plus or minus 1 on the proton channel and or independently plus or minus 1 or 0 on the nitrogen or carbon channel. And that means if you look at your triple resonance pulse sequences or an HSQC, the phase shifts are almost always just X and minus X. And a 180-degree phase shift is easy to understand why the receiver has to change from X to minus X, because the sign of the magnetization obviously is being inverted. This phase cycling theory is most powerful if you're thinking about double quantum filtered experiments, triple quantum filtered experiments, 2 quantum experiments, 3 quantum experiments, because it lets you avoid writing out every step of the pulse sequence and doing the calculation and adding everything up. In any event, here's a proof of the statement that if you shift the phase of the pulse, you change the phase of the coherence. And now, this is saying the same thing. And this simply says that if we keep track of the phase shifts through the whole experiment, we just need to shift the phase of the receiver so that this becomes unity. So the phase of the signal we want plus the phase of the receiver is 0, so that the complex exponential will become e to the 0 as well. And then we hope, if we've arranged this properly, that this summation for the signals we don't want will go to 0. And here's just a very simple example, which is basically what I just said. If I apply a 90-degree pulse, and the receiver is this black dot, and I phase this to be absorptive, if I then apply a Y pulse, the magnetization is 90 degrees out of phase with respect to the receiver, and I'll see a dispersive signal. And if I shift the pulse phase again, I'll get an inverted absorption signal and then inverted dispersive signal. If I were to add these 4 up, I'll get 0. But that doesn't surprise you. You probably have the experience accidentally. You apply the X pulse, a Y pulse, a minus X pulse, a minus Y pulse, add them up and get nothing. If I want something to happen, when I shift the phase, or I could shift the phase of the receiver, it does the same thing. If I leave the pulse alone and shift the phase of the receiver, all that's important is the relative phase between the magnetization at the start of acquisition and what I'm calling the receiver phase. This will also then generate signals that add up to 0. And then if I want to accumulate the signal, every time the magnetization is shifted in phase, the receiver has to shift in phase to follow. And then I'll get the same phase signal every time I can add them up. And I get a signal. Now, on a modern spectrometer, in fact, 90-degree phase shifts are what's done almost all the time, 90 or 180 degree. And it's not actually done by shifting any phase of anything. A 180-degree phase shift of the receiver just tells the computer subtract the two transients rather than adding them. And a Y phase shift means swap the real and imaginary parts and then add it to the first. And a minus Y phase would mean swap the real and imaginary parts and subtract them from the first. Yep. So you will only detect coherence order -1. Anything else that you end up with won't be detected. So your pulse sequence has to have the last pulse generate what you want at a -1 coherence order. And then that last step, you get the selection for free. All the other coherence orders can't be detected. But your last pulse has to make sure that you transfer magnetization from whatever operator you had to at least partially to -1. Otherwise, your experiment doesn't work. And then the only rule is also kind of obvious, that there's periodicity here because the phase shifts go around in 2 pi, and that means phase cycling has a periodicity to it. So the rule becomes that if we have phase shifts that are given by 360 degrees divided by n. So if n is 4, you're shifting the phase of a pulse by 90 degrees. If n is 2, you're shifting the phase by 2. If n is 8, you're shifting the phase by 45 degrees. The periodicity means that you can pick out the values of delta p plus 1, delta p plus 2, blah, 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 up to delta p plus n. But then delta p plus n minus 1, but delta p plus n will also be selected. It becomes degenerate because of the cyclic nature of this. So if we need to distinguish more values of delta p, the change in coherence order, then we need more steps in the phase cycle. And if we need to distinguish a fewer number, we need fewer steps. And that's basically the only rule here, is if we want to pick out +2 and distinguish it from +1, 0, and -1, a 4-step phase cycle will do, but we'll also detect -2 as well, and +6 and -6. Now our pulse sequence might not excite -6 quantum coherence to any appreciable degree, so we might not care. It could be that we want to keep both +2 and -2, in which case the 4-step phase cycle is fine. If for some reason we only wanted +2, we would need a 5-step phase cycle. So that we would reject -2, and then -3 would be the next one we would be selected. So the only key part here is figuring out what coherence orders are excited by your phase cycle and working out how many steps you need in order to reject those that are important to you to be rejected. Because exciting very high orders is difficult. And then one works that out for each pulse and then designs the phase cycle for the receiver to pick up the one you want. And as long as at each step the phase cycle on a given pulse or block of pulses is sufficient to select out only those coherence pathways that you want, at the end, you'll be done. You'll have the coherence pathway designed for your experiment. Now, these quickly become, if we have many, many pulses, you quickly get very, very long pulse sequences. Because if you have 3 pulses, and each one needs to be cycled in steps of 4, then you need 64 steps if each is going to be cycled independently. And then to make that shorter, you have to start thinking about, are there pulses I can cycle together as blocks? Or maybe I don't really need 4 steps because here, for example, if I switch to 2 steps, I would also pick up the coherence order 2 level. But maybe I know in my experiment that coherence order 0 just doesn't have very much amplitude. And I don't need to worry about it. So I might be able to shorten the pulse sequence, the phase cycle, by thinking more carefully about what's actually happening. This is guaranteed to work, but it might generate too long a phase cycle to be practical. The shortest phase cycles, general phase cycles, without knowing the fine detail of a particular experiment, are what's called cogwheel phase cycling by Malcolm Levin, which is so elegant that I think it's hardly applied in practice.
And they're kind of long, basically. You don't need to do this thing.
So here I'll just tell you 2 famous phase cycles, and then we'll end. So in the early days, pulses weren't very good. There were artifacts from the phase shifts. And this phase cycle called Cyclops was invented. I don't remember why it was called Cyclops. And do you remember why it was called Cyclops?
I don't know.
I mean, people spend a lot of time thinking of acronyms for NMR. So it means something. But it simply takes the receiver X, Y, minus X, minus Y, tracking the pulse, which is doing the same thing. And this will suppress imbalances between the receiver channels. If X and minus X aren't identical, X and Y are identical except for the phase shift. This phase cycle will help cancel out those artifacts. It's not so important anymore because spectrometers are so stable. But if you look inside the typical pulse sequence, there's probably some pulse that's going X, Y, minus X, minus Y, more or less for historical reasons. And then the other is called exercycle, which also stands for something I don't remember. And this was to try to clean up artifacts of 180-degree pulses. And you'll still see this used a lot. If not the full phase cycle, then half of it. Because as we've said many times, 180-degree pulses aren't very good. They have lots of offset artifacts, etc. So if we have a 180-degree pulse, what we wanted to do, so suppose we have I plus magnetization, a 180-degree pulse should take I plus perfectly to I minus. But if the pulse is imperfect in some way, we'll keep some I minus, we'll generate, or keep some I plus, and we'll generate some I equals 0 coherence. And after the pulse, we will generate a magnetization that we don't want. An exercycle is a simple phase cycle in order to suppress these other transfers. And this phase cycle will do it. We have this 4-step phase cycle, and the receiver just goes X and minus X, and that will do the trick. So the coherence order change, for example, shown here, goes from +1 to -1. So the coherence order change, delta P, is -2. We shift the phase by 90 degrees. The receiver phase has to shift by -180. 2 times -2 times 90. And a minus 180 phase shift is the same as a plus 180 phase shift. We don't need this thing. So every time the pulse phase changes by 90, the receiver phase changes by 180. And any magnetization that ended up at coherent order 0 or stayed at coherent order +1 will get null over the phase cycle. And again, if you look back at older sequences, the sequences will be very long because so many 180 degree pulses were cycled before step exercycle phase. One of the main uses of gradients, in fact, is the same suppression happens by surrounding the 180 degree pulse by 2 gradients. Because on one side, we wind up the magnetization, say, with a positive sense. On the other side, we've reversed the precession sense, and now we unwind the gradient, and anything that ended up on 0 or stayed on +1 doesn't get unwound properly. So the gradient, one of the main impacts of gradients, is that to surround all the 180 degree pulses with pairs of gradients to clean up these artifacts. The one would have had to have been cleaned up before step exercise. But still, if you look at the most critical 180 degree pulses in the pulse sequence, you still might find exercycle phase cycle, even if there is a gradient nearby, just to make sure that 180 degree pulse performs absolutely as well as possible. Okay, we run a little over, and I have to get to the airport. So we'll stop here. So